Hi, I'm Matt Gaska. I'm an engineer with Siemens, and I'm going to talk about how to use the trace tool and operate today. So the first thing we're going to do is we're going to just quickly drive my axes to some known position, just my x-axis, because I have comp enabled on this axis. I'm going to show you some positioning traces. So we're exactly at 8 to start. So we come into diagnostics area, and I'm going to make a brand new trace. The name doesn't need to be anything unless you're going to be saving it. We're going to start off saving NC variables. I'll explain what the rest are later. And now I'm going to add a new variable. So if I want the position coming off my encoder, there's basically two groups of stuff for an axis. There's the axis stuff, which is the axis has a ball screw, axis has a gearbox, it has a scale, it has all that kind of good stuff. And then there's the servo, which is the drive side. So the servo side is going to be my raw encoder value. So I'm going to search, pick servo, pick position, get a bunch from here. Now where it says measuring system 1, measuring system 2, this is your motor encoder and your scale. Typically measuring system 1 is your motor encoder, typically measuring system 2 is your direct, your linear scale, or in the case of a rotary axis, your direct encoder. Position set point is the command. So this is the encoder values are here. The set point is the command. Now the thing that's going to be a little funny about this is even though it says set point, this is going to be the uncompensated set point. Quickly show you. Sorry. In axis diagnostics, service axis, I've got a little bit of comp push in here, about 40 thou. And I've got, so that shows up even though you just saw me drive the machine all the way to exactly 8. We're at exactly 8. We've got 40 thou comp, so my encoders, after the ball screws applied, is reading 796 with my 40 thou comp. Go to trace, add my encoder position, pick my axis, I'm going to do X, and then I'm just going to quickly hit start so we can see something. Let's say view trace, because I don't have a start button here. Start. And I'm going to get a couple seconds, 10 seconds worth of data. It's 10's the default. Okay, so now this looks like a whole bunch of gibberish because it's taken up my whole screen. I can manually scale this, or I can say fit all. So if I had more than one trace, it would overlay them nicely for me. What it's doing is it's basically just zooming out to the extents. So I'm going to change my scale. I'm going to go from 7.5 inch up to 8.5. I can just type that in directly, say finish. And what we see is the range of what I just traced, because I wasn't moving, we don't have any fancy waves. It looks at like it's staying right about 796. If I fit all again, it's going to zoom in based on the range of what we had. And what we can see here is that since I have a real encoder hooked up, we're getting just encoder ticks as the motor is trying to hold position. It's moving basically from one side of a reading to the other side of the reading, and it's basically idling. Now, this is kind of interesting, but a little bit boring. Let's add some more data to this. So, if I add my set point for my x-axis, view trace, start that, collect it. Because the set point doesn't have the actual encoder on it, we don't get that little bit of jitter. Okay, so now I'm going to say fit all. This looks more interesting this time. What it did is it took my set point, which is sitting at 796, just a fuzz below 8 again. It's going to be one nice solid line because I'm not commanding a move. And then I get my little bit of deviation from my encoder sitting, trying to maintain position up on the top. That's what this fit all button does. It's a quick way to overlay your axes. What you have to watch for with this is that as I change between traces, I'm using a mouse and I'm clicking up here where the numbers are. If you don't have a mouse, you use the tab button on your operator panel. But you'll notice that the scale on the left-hand side is different. So in this case, I've got, what is it? Not even a full thou of an inch from my top to bottom, my range. Trace 2, I have, 4 inch there. That's my range. Let's say that I wanted to take these two axes and overlay them so I can see them relative to each other. What I'll do here is I'll come in and I'll hit Scale, and I'll hit Selector. Any traces I select now, these are going to get the same scale applied to them. So let's say I want to do my range from 7.9 to 8.1. And we'll say Finish. It's zoomed in. I need to zoom in a little bit farther because they're overlaid on top of each other too tightly here. Now I could go back in there, or I could come into the zoom function, and I'm going to select that I want to change my Y value, and I will start clicking on zoom and only zooming in Y. You'll notice that my X scale is not changing, my Y scale is. And we're almost to something useful. Okay, now what we have here is we have what I was going for, which is I wanted to see my encoder signal and my set point overlaid on top of each other. As expected, my set point doesn't change, but my encoder signal is bouncing off of each side of the encoder tick marks in the encoder, so it's just sitting there dithering. And if we wanted to see the magnitude of these, because now that we have them scaled so they're both the same, if I go between either trace, I can see that I have the same scale on the left. Let's say I wanted to get a numeric value for this. I can use cursors. So I get two cursors, an A cursor and a B cursor. I'm going to select my first trace because that's what I want to have the cursor bouncing on. And you can use the left and right keys on your operator panel. This is a little too hard to see. So what I'm going to do is I'm going to change my scale so I'm only looking at the first 0 to half second. Again, it scaled both of them the same for me. Go back to my cursors. So I can see that I've got my A cursor, and we can see the values of where is this cursor. Right now I get a time and a value. So I could write down two numbers and try to do some math and find out what the deviation between those peaks is, but I'm really lazy and I don't want to. So I'm going to turn on a second cursor, cursor B, move that somewhere, and then I'll get that in position. Now I'll say both cursors, and what this does is B's down here. Where did I leave A? A is up there. You can toggle between which one you're controlling. But now that I've got both of them up there, you may have to move the cursor once or twice just to get the screen to refresh. But right down here, it gives me the differences between A and B. So it gives me the values of where's A, where's B, and since I'm too lazy to do math, it gives me the differences between them. So something on the order of 10 to the minus 6 inches, that's 6 millionths of an inch. That's encoder resolution, and generally that should be expected from a motor sitting still if we're looking at the raw encoder signal. So what I showed you so far was just the general concept of let's grab some data, let's plot it, let's look at it, let's see some numbers. Now let's talk about different types of things that we can grab with this tool. I go back out. Now we've got different variables we grabbed here. So I started with insert variable, and I picked a couple of my positions. Now, one of the things that you're going to see is that if we say all variables in this, one of the good things is that this tool is incredibly powerful, and there are 10,886 variables available for me to trace, which is more than a couple, which is why we use the filters. Even if we just search for position, we're still going to get 262, which is why it's useful to have some kind of quick lists of stuff that you use often, which are things that I'm going to start going through here. Is in the servo values, we have the encoder raw encoder values. This is the position command without compensation. and in axis variables, because this again is the separation between the drive side and the NC side, we have quite a few other positions. Now, what we're going to pick out is a variable called tool actual base position. This is the command. So when I trace this, we're going to get that 8-inch value of where are we sitting. This is the compensated position. So I'll add that for my x-axis. Now I get a new one. It's grayed out because I haven't added any data to it. And take my machine out of E-stop. Go back, make sure I'm still sitting at 8. Not quite. Drive back to 8. And we'll do another quick trace. So we'll just say view trace again. Start it. This time I'm going to get the third value. It's still keeping some of my scaling from the previous run, which unfortunately means that the command value sitting at 8 is well off my screen. It's up top somewhere. So I'll say fit all just to get a quick overview. And if I click on third trace, we can see it's dead at 8. My position set point with the uncompensated one is still at a little bit less than 8, 40 thou, and we still get my jitter coming off of the motor encoder actually moving. Well, not jitter, just dithering. Jitter's a timing thing. So I used the wrong word. Sorry. So we go back. I'm not grayed out anymore because I now have data. And let's take a look at, let's say I didn't know this actual tool-based position, but let's say I knew things like, let's say I'm a programmer who knows a lot of the system variables that I've been using for years. I'm allowed to just type things in here. Like, for example, if I want to read the machine axis position of an axis, this would be a variable we can get at in a part program. I can type that in here and it'll work just fine. So what I did, because I know a lot of the system variables, these two variables, these axis command, axis set points, happen to be the same thing. It's just two different ways of addressing them. If you have a mouse, you can change some of these column widths, and it's the same variable internally. It's just two different paths to get at it in software. But since we can type stuff in freely, I'm going to add a PLC variable. In my case, I'm going to add input byte 3, which includes the feed pot from my machine control panel. Same thing, I can do I3.0 and get just a single bit. I'm going to throw this one out by hitting delete because it's just going to make things messy. And so we'll go ahead and trace some of these. So view trace, E-stop again. I could do these in E-stop if I wanted to. Let's say start trace. Sitting there, put a feed pot. We don't need to collect 10 seconds worth of data. And in my selector, there's two ways I can do this. Let's say I wanted to see everything. I can either go through and pick the extra 3, or I can deselect the 2 I have chosen. I can say fit all and get my nice spread again. I don't want to look at my top and my bottom variable right now, so I want to see my encoder position and my PLC byte. The reason that somebody would want to do something like this is if you're trying to figure out some kind of timing problem between a sensor or an actuator and some axis motion, this is a convenient way to overlay things. And we'll say if it's selected, we get a pretty decent view. This is generally going to be the easiest way to look at stuff, but let's say I wanted to change my scale, so I only want to see 1 to 2 seconds. There's 2 ways to do this. Turn off the selector and say zoom in my x-axis. And that can work pretty decent. So let's keep zooming in. And what we're going to see is that it looks like I have a lot more transitions on my NC data compared to my PLC data. Yes, that's completely correct. The reason that this is happening is because we're working off of 2 different scan cycles. The logging cycle for NC data is, in this case, happens to be at 2 milliseconds. The PLC scan is closer to 30, and we'll talk about this later. But what I want to show you next is, let's say we didn't want to just use the zoom buttons. I'm going to show you why we use the zoom buttons instead of trying to do this by hand. Because if I wanted to do this by hand and use a scale function at this point, which is what I suggest you don't do, is I can come back to scale. I have my selected waveforms. The hassle being now that I want to set go from 1 to 1.5 seconds. Picking up something out of a hat. The hassle is that my y-axis values for both traces is from 1 to 50, which is not what I wanted. I wanted things that were where I could see both of them. So let's say finish, and if I hit fit selected here, it's going to zoom out my X range, which isn't what I want. What I want to do is what I want to do here is I want to zoom in on my encoder signal. So what I have to do then is I have to go back to my selector, turn off my PLC function because it's going to be on a different scale. I'm going to change my scale for my y-axis, and that's going to be 7.96 to 7.96001. Try that. 7.96. Now, what I really don't want to do here is I don't want to use any of my arrow functions. So, like, I could use my arrow keys on my keyboard to move this trace up and down. The problem is that it's going to also shift my PLC signal at the same time, and things are going to be a little problematic looking. So if I'm in here and I'm moving both of them, that's great. The hassle being that if I was doing this with both of them, one of them deactivated, the one in the background would also be getting updated, I might lose stuff. But we can clearly see what's going on. So we wanted to talk about timing of signals. Let's go back. So one of the things that we get is I showed you that we can resize things. If you have a mouse, resize the columns. You can change color of the traces. Where it says pen, this is what kind of line type do you have? Do we have dashed lines? Do we have just markers? Are we showing or hiding it? I didn't want to see all of them. The next column over is what event are we using to log our signal? So in the case of the servo cycle, that's typically 2 milliseconds. That's the communication between the NC and the drives, not the interpolator cycle. That's here. That's going to be much faster. Same thing, I have my PLC scan cycle here. Different variables can be logged at different rates. The availability of which one can you use more or less depends on which signal or which processor you're getting the signal from. And in general, when you pick stuff out of the list, or even when I just typed in variables, it automatically selects this for me. So you don't have to worry about it too much in the context of, do I need to know which one I can use? You just need to be aware that you might have different events going on. So for example, if you are doing a trace like I just did, where we have some PLC state that we're trying to watch, it's entirely possible that you will get I/O state changes that happened while you couldn't observe it, even though you may have seen something moving. It's possible the data just isn't observed because you're running at different sample rates. This is also a reason that if you're looking for things such as enable states of an axis, let's say insert variable, and state. Okay, so we've got the pulse enable for the drive. If I add this, and again, I can pick any axis I have in my system, this is going to be logged on my interpolator cycle. The alternative would be that we could be pulling this out of data block 31 for an axis. We would want to use the one from the NC on the interpolator cycle because we're going to get more, that's going to be updated to the trace more frequently than if I pull it from the PLC. So in general, this is a good thing. Now we want to talk about timing. One of the things we can do is there's some settings and options here. Under settings, one of the things that I can do is we can change the sample rates. The reason we would do this is that, let's say for the interpolator cycle, or the servo cycle, things that are being logged quickly, as we start adding more and more data, the capacity of the system to log data and manage data starts to get limited. Sometimes what we can do is slow down the sampling rate, and we can collect more data reliably. If we're collecting too much data too quickly, you'll see vertical bars on your trace, and you'll see a message with the effect of data lost because of buffer problems. So we can change our sampling rate here. So even though we are logging at the epo cycle, I can change it to, instead of the 4 millisecond epo cycle, anything that would have been logged on that, I'm logging at 8 times or 32 milliseconds. Let's not do that. What you'll also see here is we have a couple of different ways we can start. Now, everything you've seen me do so far, I've just been opening up the view trace and hitting start, and it starts logging. Great. And it's been running for 10 seconds because 10 seconds is the default. I could let it run until I hit stop, or I could let it run until we run out of some amount of memory. Like, let's say I wanted to say that we can only want to have a 512 kilobyte file. Okay, whatever, that gives me about 14 seconds. This is always a bit of a guess because it does some data compression as it's running, so this is more of a minimum than a maximum. If you really want a timed value, use elapsed time. You can also do things to trigger a stop condition on some event, like if you press the reset button. So like 3.7 is the standard mapping for the reset button on the machine control panel. Whenever that equals 1, I want to stop my trace. Or I could also do whenever it's rising, which would actually be a better case in a lot of instances, is instead of watching the state, watching for an edge is usually better. We can also start recording based on a trace trigger. So instead of me just waiting to hit the start button, I can do this based on some kind of like an axis position exceeding some threshold or a velocity. There's also a part program trace trigger. So if I wanted to start the trace when I reach such and such point in a part program, I can use this variable in a program to start it. Same thing, I can use it to stop it. The most common thing to do with it is use 1 to start it, 2 to stop it. I'll also been known to use rising and falling edges and do 0, 1. But if I go to MDA and write a quick little program, that would just be $and SL trace 0 at the start of my program, G0X0, start it with it equal 1, stop it when it's 2, we'll run this program. So we've got that program set up. Go into diagnostics, back to my trace. Again, this quick list will give you all the things you have in your trace plus the variable if you've forgotten what it is. So if it equals 1, stop it if it equals 2. Okay, you trace, hit start. Now it's sitting here idling, waiting for that trace trigger. So take my machine out of e-stop, hit cycle start. Now my program's running. It started the trace for me automatically. Program finished. So we just had the simple little program. And then I will do I'm going to turn all of them on. Do fit all. Oops. Trace. Again, these guys are toggle buttons. I've been caught on that more than once myself. And we get a nice trace value, and we only got a chunk of data. We got from 0 to about 0.8, 0.9 seconds. And then because we had this post triggered for a half second, means that we got more data at the end. And you can use this to set up your own timing so that you don't have to be as quick on the buttons. The nice thing about the way that this works is because you're allowed to keep large amounts of data, especially if you have a PSU50, these traces can run for minutes or hours. Typically, once you start getting above a few minutes, it becomes a little bit hard to deal with just in terms of navigating. But if you do need a longer trace, you can get it. So we'll close out of that. There's an options page. One of the things that we can do is we can save traces. This checkbox here, XML is the default format. You can also include a CSV file if, for example, you wanted to bring this into Excel and do some of your own analysis. So if we check this box, we're automatically going to generate 2 files every time we hit save. We haven't saved one yet, but that's creatively the next 2 buttons down. So if I want to hit save trace, do I want just the stuff that I've used to set it up, or do I want the values too? Choose those with the toggle buttons. And this will save it, in my case, to the CF card, even though it has the .xml extension, because I checked that other box. It'll also save it to as a CSV. So I saved it off as demo. I can go under setup, go into my system data, and if you do like me and you forget where the default is, come back to diagnostics, hit save, and you get the path right here. User SINUMERIK HMI data trace. User SINUMERIK HMI data trace. So as promised, we get the CSV and the XML value of both files both. Control C and Control V, and you can copy them off to a file server or USB stick or whatever you need. The other thing you can do is, when I'm doing a lot of traces, I'll often change this folder to my file server so that I don't have to go digging for all these. It just automatically dumps them off. So it's your choice. So that's the basics of the NC servo trace. Now, there's a different type of trace. When we hit new trace, there was a radio button I didn't talk about. We have the ability to grab what are called drive variables. This is the stuff that is in the control units, in the drives themselves. One of the limitations of this is we're only allowed to grab from a single NX or control unit at a time. So for this demo, I put 2 axes on my NCU, I put X and Y on my NCU, I put A and C on an NX15. So I'll pick the NX15 just for fun. And now I hit insert variable. I have a completely different screen here in terms of what I have available. I don't have the filters that I had before. I can't see my x-axis because my x-axis is on my NCU. So at the point where I made that selection up top, that was when I got to decide which axis do I get to see. If I needed to see my x-axis, I'd have to cancel out of here, do a new trace, pick my NCU, insert variable. Now I can pick off my x-axis, but A and C are gone. So let's say, for example, I needed to get my variable 63, which is one of the velocities. That's what I wanted to trace. Okay, that shows up. What I can do now is, if you remember when we went into settings before, we had clock rates that were like 2 milliseconds, 4 milliseconds, and things of that nature. Now I have my speed loop clock, which is 125 microseconds, which is generally very, very fast. But that's 16 times faster than my 2 millisecond rate. So depending on what you're doing, sometimes you want very, very fast data to look for oscillations, or sometimes you just want access to very raw drive data. Either thing works here. If I'm doing something where I don't need the speed and I'm just trying to look for drive variables and get direct access to those things, I'll usually slow this down with the 16x multiplier because then it allows me to get a longer trace. Because what you'll see here is, let's say I leave this at 1 at my storage limit. Storage limit is 90K. That gives me about 3 seconds for one variable. If I add a second variable, it's going to cut this in half, and I'd be at 1.5 seconds total. Or what I can do is, let's say I want to do about a 15-second trace with just the one variable. I can increase my sampling rate, and now I can get 50 seconds. So you have choices. The same kind of thing will happen is if you're just playing with the time here. It'll, let's say I added 100 seconds. It's going to tell me I don't have that much memory. But this is available for faster things or for access to parameters in the drive. And if you'll notice, if you look at insert variable, pretty much everything in the drive that's available for reading is listed here. So a lot of the actual speeds coming off the encoders. These are raw, unfiltered, coming at you at 8 kilohertz. That's quite a bit of data. It's quite useful. So now we're going to look at one of the limitations. We're going to go back into our settings. And if we look at our trace triggers this time, go to our quick list, we only can trigger off of variables we're tracing. We can't trigger off a cycle start anymore because that's in the PLC scope of traces. When we selected what type of trace we're doing, we selected we're doing drive trace, we can't get at that anymore. We're basically just using the control unit itself as the trace tool. Same thing, I don't have that $AN SL trace variable anymore because that's an NC scope variable. It's more limited here, but the benefit of working with these drive traces is the speed and access to variables that are not otherwise available. Now, there are some variables that are available in the NC trace. So we'll go back there. One of the variables we're going to look at is called load. What this is this load is, it's a percentage, again, we can pick any axis out of the list. It's a percentage of what they call drive utilization. Now, drive utilization is a little bit of a incomplete term. This should be a whole sentence because it's a composite. It's not just what percent of my current am I using. It's a composite of what percent of my current am I using, what percent of my power am I using. There's several different things that come into this. And the reason that you would trace drive utilization is, let's say you're looking for, am I being limited by the fact that I'm just running out of juice being a technical term for the composite of power and current and everything else that a drive can be limited on, and it'll automatically pick up and use the lower limit of the drive value or the motor value. So let's say that you have a motor which has a 1.5 amp capability, the drive has a 3 amp capability. It'll use the 1.5 value instead of the 3 because you're going to be using more of that. So all this is bundled up in utilization, and what you would use this for is to see if you're just running out of juice and you can't get any more out of the drive or motor. And what you'll see is that when you run that, you'll see a flatlined response on the top. Now, what I prefer to use for a lot of testing is I prefer to use a variable called torque. I believe I have to go to servo for this. Torque producing current. The reason I like to use torque producing current is that this is going to be a number in amps. And the reason I'm specific about I don't just want the total current, I want the torque producing current, is that with various motor constructions and limitations, you can get into cases where some of the current that the drive is sending out is used for field and magnetism related things related to the winding. So like if you're in a field weakening range on a motor, or if you're dealing with an induction motor, there's current being used to make the motor big magnetic, but that's not actually giving you force or torque out of the motor. If you're on a linear motor, all the words change to force instead of torque because straight versus round. But the point being, with the torque producing current, this is a good thing to use to see, like let's say you have some kind of obstacle that you're running into, and you want to look and see how does the machine behave over the length of an axis travel. You would look at the torque producing current, and you could see that, oh, in such and such area or at such and such distance, I'm building up and I need more torque. That may not be realized in this utilization value because there may be something else that's closer to its limit, so it'd be hidden there. The other nice thing about torque producing current is that it also has a plus and a minus sign. So for the example of a vertical axis, one of the reasons I use torque producing current is because it's signed. Now, the nice thing about it being signed is that there's things that you can expect to see. So if you have a vertical axis, you should expect that it's always going to have to be pushing up if you don't have a counterbalance, because you have to keep it from falling. Unless you're accelerating the vertical axis over at 1G, you're always going to be pushing up. If you see that it has to start pushing down, that means that you've probably got some kind of binding in your axis. That can be problematic. Another good value to trace is what's called contour deviation. So just search for contour. Contour deviation I'll throw this one up there as well. Is a similar value to following error. Following error is the difference between the actual position and the commanded position. So that is again a composite of not only things that are caused by mechanical disturbances in the system. Like let's say you have a rack and pinion system. Every time you transition between teeth, you're going to expect to see a little bump in the following error, just as a matter of going to tooth transfer. But it's also going to have all your servo lag built into there, so you're going to have a couple things stacked on top of each other. What contour deviation is it's the difference between the expected following error and the actual following error. So when we say expected following error, at any given steady state velocity, constant velocity, based on the gains that we have for the axis, we can calculate what an expected following error should be. Sometimes the models are very good, sometimes they're not. But what contour deviation is it's what's left over between the expected and the actual following error. The reason that this can be very, very valuable is that if you're looking for a spike, like I just described with the tooth transfer problem on a rack and pinion, if that's what you're looking for, because you already have the steady state following error component removed, it can be very, very helpful because now there's less stuff to look at. The thing that you have to watch with contour deviation is that as a value, the way that the models are run, you should not compare contour deviation from axis to axis. You should be if you're looking at the x-axis contour deviation versus the y-axis contour deviation, there are many cases where that's not necessarily a representative way to look at it. That will get you a good value. There's some scaling things that go on. And because of the scaling, anytime you make a change to a control loop or change axis, you kind of have to stop using that as a comparison of this versus that. But what it is good for is, let's say we've got the rack and pinion example again, and we're making no software changes, and we changed our pinion engagement. We got the wrenches out, we turned something tighter, we turned something looser. We'll see a change in contour deviation. We can see that it got better or worse. That's a useful value. We can't. You can use it kind of as a percentage, but you don't want to use the absolute value that says, "Oh, well, my contour deviation showed up as 20,000, now it's down to 10." That scaling may not always be correct, but you can use it for comparison purposes. Hope all this is helpful to you, and good luck to you.